In this problem session, I'm going to review some of the old test questions that I've asked over gases in the past. So we're in Chapter 4, Practice Problems on Gases. Now, before we start these problems, let's quickly summarize all of the gas relationships that you need to know. Okay, so first of all, we have some of the simple gas laws. So here are some of the simple gas laws that you need to know. The simple gas laws include, first of all, we have Boyle's law. Boyle's law says that the pressure of a gas is inversely proportional to volume at constant temperature. Now, here's how I remember this. The mnemonic for remembering this is that you can say water boils at constant temperature. Water boils at constant temperature. So if you hold the temperature of a gas constant, what happens to, if you hold the temperature of a gas constant, what happens to its pressure compared to its volume? Well, as you compress a gas, the smaller the volume, the greater the pressure of the gas will be. And so that should make intuitive sense. That's Boyle's law. Charles's law is the second law that you need to know. Charles's law says that under constant pressure conditions, the volume of a gas is directly proportional to its absolute temperature. This is at constant pressure. And the way that I remember this is that I remember the story of Jacques Charles. Jacques Charles was a hot air balloonist. He discovered that if you heat up a gas, its volume expands, and that's how a hot air balloon works. And then we have Avogadro's law. Avogadro's law. Now, when you hear Avogadro's law, when you hear the word Avogadro, you think of a mole. Avogadro's law says that volume of a gas is directly proportional to the number of moles of a gas at constant temperature and pressure. At constant temperature and pressure. If you keep the pressure and temperature constant, but you double the number of moles, you double the volume. Okay? So that's the first set of laws that you know. Secondly, you need to know the ideal gas law, and we'll be using these. The ideal gas law says PV equals nRT. PV equals nRT. One way or another, you're given three of the four variables. There are four variables here and one constant. R is a constant. One way or another, you're given three of the four variables and you're asked to solve for the fourth variable. The third relationship that you need to know is the combined gas law. This is very useful if you change the conditions of a gas. The combined gas law, which says P1 V1 over N1 T1 equals P2 V2 over N2 T2. So that's the combined gas law. If you have a gas under one set of conditions of P1 V1 N1 T1 conditions, and you change those conditions, then you can use the combined gas law. Next, the fourth one that you need to know Dalton's law of partial pressure. You need to know Dalton's law of partial pressure. So Dalton's law of partial pressure says that if you have a mixture of gases, then the total pressure of a mixture of a gas is equal to the sum of the individual partial pressures. So if you have gas A, it'd be the partial pressure of gas A, plus the partial pressure of gas B, plus the partial pressure of gas C, plus ... So this represents, these values represent the partial pressure of a gas in a mixture of gases. You add them all up, that gives you the total pressure. Another way to express Dalton's law of partial pressure is that the partial pressure of gas A is equal to capital X sub A, which stands for the mole fraction of A, times the total pressure. So you need to know that capital X sub A stands for the mole fraction of A, and using our junior high definition of a fraction, the part over the whole, then the mole fraction, if it's the part over the whole, if it's a mole fraction, what's the part? It's the number of moles of gas A. What is the whole? It's the total number of moles. And the possible values of a mole fraction, of any fraction, the possible values are 0 to 1. And then finally, the last gas law that we will be using that you need to know, number 5, is Graham's law of effusion. Graham's law of effusion. And Graham's law of effusion says the rate of effusion of gas 1 divided by the rate of diffusion of gas 2, or this is the ratio of the rate of diffusion of gas 1 to that of gas 2, is inversely proportional. This is equal to the square root of the molar mass of gas 2 over the molar mass of gas 1. So capital script M stands for molar mass. This is the rate of effusion of gas 1, the rate of effusion of gas 2, the molar mass of gas 2, the molar mass of gas 1. In the examples that we will be working, I'll be able to illustrate each of these laws. So let's go to our practice problem set. This is on page 145 of your lecture notes. We'll start with this first question. A gas bottle contains 0.650 moles of gas at 730 millimeters of mercury. If the final pressure is 1.15 atmospheres, how many moles of gas were added to the bottle? Now, notice that you're adding a gas to this original. So how many moles of gas were added to the bottle? Okay, so in this case, we're going to use the relationship P1V1. I'm taking a gas under one set of conditions of P1V1 over N1T1, and I'm going to change the conditions P2V2 over N2T2. Okay, so this is the combined gas law. Okay, and so if we just notice what we have, that first of all, this says assume that the temperature remains constant. Well, if the temperature remains constant, then that means T1 is equal to T2 is equal to a constant. What can you do if you have a constant on both sides of the equation? If you have a constant on both sides of the equation, then you can cancel it out. So T1 cancels. Next, notice that it's in a gas bottle. It's in a gas bottle. You're adding gas to the bottle. The volume is also constant, even though this problem doesn't explicitly say it. If the gas is in a bottle and you add more gas to it, then the volume of the bottle remains constant. So V1 equals V2 equals a constant. And what can you do if you have a constant on both sides of the equation? You can cancel it. Okay, so as you look at this, we know the original number of moles is 0.650 moles. The original pressure is 730 millimeters of mercury. And then we have the final pressure. So let's find the number of moles of gas 2. Now, I'm going to cross multiply. In fact, we can talk about the algebra here. The algebra that's involved can be looked at this way. If you have the relationship that A divided by B equals C divided by D, then in terms of algebra, we can swap those two, or we can swap these two in order to isolate something. Let's say that we want to solve for D. If we want to solve for D, we can bring D up here, D equals, and bring A down here, so C over A, because C is still on this side. I'm bringing D up here and swapping D and A, and I'm going to bring B up here times B. D is equal to C times B divided by A. So that's one way that we can go about solving this. Now there's another relationship that we'll be using, an algebra relationship. If you have the relationship A divided by B over C divided by D. Well, this is sometimes called the horseshoe rule because this is shaped like a horseshoe. So that this is equal to A times D from the horseshoe in the numerator, AD, divided by BC in the denominator. So that will help us. But in this case, we're solving for D. It's in the denominator. Look at this relationship. I need to know what N2 is. I'm going to bring it up here and bring P1 down here. So N2 is equal to P2 over P1. So I just swap those two, and I'm going to bring N1 up here times N1 in the numerator. So when I plug that in, now in this type of relationship, I can use any unit for pressure as long as I'm consistent. Okay, so the original pressure is 730 millimeters of mercury. The final pressure is 1.15 atmospheres. We are going to have to watch the units and make sure that those are used appropriately. So the final pressure, let's write the units, 1.15 atmospheres, times the original number of moles, 0.650 moles, divided by the original pressure. The original pressure is 730 millimeters of mercury. Now that reminds me of something I should have added to your sheet that you need to know. You need to know back over here, if we're listing the things that you need to know in order to deal with gases, you need to know that 1 atmosphere is equal to 760 millimeters of mercury, Or we can say 1 atmosphere is equal to 760 torr. Both of those statements are true because 1 torr is equal to 1 millimeter of mercury. These are all units of pressure that are frequently used in chemistry. Another relationship you need to know is that the temperature in Kelvin is equal to the temperature in degrees C plus 273.15, because we're going to have to convert all of the temperatures to Kelvin when we deal with gases. So I have atmospheres in millimeters of mercury. They don't cancel. But I know this. I know that 1 atmosphere equals 760 millimeters of mercury. So I can use that as a conversion factor. I'm going to say times, and in the numerator I'm going to put the millimeters of mercury, 760 millimeters of mercury, so that it will cancel this millimeters of mercury, and in the denominator 1 atmosphere. So you see atmospheres cancels atmospheres, millimeters of mercury cancels millimeters of mercury, and we end up in units of moles. This calculates out to be 0.778 moles. Now, you should always answer the question that was asked. This says, how many moles of gas were added to the bottle? So we started with 0.650. We ended up with 0.778 moles. So how many moles were added? So to answer, I'm going to put right here, let me use a different colored pen. This will answer our question. Therefore, the number of moles added equals the final number of moles, 0.778, minus the initial number of moles, which was 0.650, so that we added in all 0.128 moles. And so the correct answer to this question is choice A, 0.128 moles were added. Okay, question number 2. By the way, in question number 1, what you're focused on here is that you have a gas under 2 sets of conditions. I have original number of moles, original pressure. Then I'm going to have add some gas. I'm going to have a different pressure. So this is the original set of conditions. These are the new set of conditions. And so you use the combined gas law. Now in the next equation, let's list what we're given. We're given the volume of this cylinder, so that the volume is equal to 43.8 liters. We're given the pressure in kilopascals. The pressure is equal to 1.51 times 10 to the power 4 kilopascals. Now notice, I mentioned in class, I'm not asking you to memorize the relationship between kilopascals and atmospheres, so you're given that in this equation, in this problem. You're given that 1 atmosphere is 101.325 kilopascals. Always watch your units. You're also given the temperature. Now the temperature that you're given is in degrees Celsius, and when you're dealing with a gas, you must always convert to Kelvin. So this is going to be 25 plus 273.15 equals 298.15. Now I'm keeping additional significant figures to avoid round-off error, but this is only precise to the ones place because this is precise to the ones place. And this says how many moles of helium are in the tank. Well, in this case, we know 3 of the 4 variables related to a gas, and so we just need to calculate the 4th variable. And to do that, we use the ideal gas law, which is PV equals nRT. I rearrange and solve for the number of moles. This is a plug and chug. Whenever you do a plug and chug, you should write the equation and rearrange the variables first before you plug the numbers in. You'll make fewer mistakes. N is equal to PV over RT. Now we can plug those in. Now notice, P is in kilopascals. Now I'll go ahead and write this, 1.51 times 10 to the power of 4 kilopascals times the volume. The volume is 43.8 liters. And then the ideal gas constant, R. You do not have to memorize any constants this semester. We will provide them on the exam. So the ideal gas constant is 0.08206 liter atmospheres per mole per Kelvin. Now, depending on which value of R and the units of R, that's going to affect your other unit. I'm going to go ahead and divide by the temperature. The temperature must be in Kelvin. You can see the unit here is Kelvin. So 298.15 Kelvin. But you'll notice that liters cancels and that Kelvin cancels. I'm looking for the number of moles, but this is kilopascals and this is atmospheres. And so I need a conversion factor. And to get this conversion factor, I need to put atmospheres up in the numerator, so that 1 atmosphere in the numerator is equivalent to 101.325 kilopascals. And so now atmospheres in the numerator cancels this atmospheres, kilopascals in the denominator cancels kilopascals. We end up with mole as our units, and so N calculates out to be 267 moles. So the correct answer to number 2 is choice B. Okay, number 3. You need to know Charles's law, Boyle's law, Avogadro's law. When I think of Charles's law, I think of a hot air balloon. And a hot air balloon, as you increase the temperature of a gas, its volume expands. So this says volume is directly proportional to the absolute temperature at constant pressure. That's Charles's law at constant pressure. So at constant pressure, the volume of a gas is directly proportional. So the correct answer is choice A. The volume of a gas is directly proportional to its Kelvin temperature. If you double the Kelvin temperature, you double the volume if you keep the pressure of the gas constant. Okay, question number 4. Question number 4 asks, what is the pressure in a container of gas connected to a mercury-filled open-end manometer if the level in the arm is 12.8 centimeters lower than in the arm open to the atmosphere? In the arm connected to the container is lower than in the arm open to the atmosphere, and if the atmospheric pressure is given as 749 millimeters of mercury. Now, what I find helpful is to draw a manometer. So here's a container of a gas, okay, and we're going to have this U-shaped glass tube coming up here. So here's a U-shaped glass tube. Now it's open here, and this says that the level in the arm connected to the container is lower, so I'll draw the mercury here, than in the arm connected out here. Okay, so just looking at that, remember that the gas inside is exerting a pressure. The gas inside here is exerting a pressure, and the atmospheric gas is also, the pressure of the atmosphere is also exerting a pressure. So which is greater? Just looking at this, you know that the pressure of the gas must be greater than the atmospheric pressure. It must be greater than the atmospheric pressure because it's pushing down further on the mercury than the atmospheric pressure. Now, the atmospheric pressure is 749, and this says, what is the pressure of the gas? Well, it's got to be greater than 749. So look, we can automatically rule out A. It can't be 128. It's got to be greater than 749. So it can't be C. It can't be 621. It's got to be greater than 749. It could be, it can't be B. 736 is also less than 749. So it's got to be either D or E. Now the difference in height right now is how you determine, this height difference is how you determine what the actual pressure of the gas is. The pressure of the gas then will be equal to the atmospheric pressure, which is 749 millimeters of mercury, 749 millimeters of mercury. Okay. And since the pressure of the gas is greater, we're going to add to this, plus 12.8 centimeters of mercury. Now, always watch your units. That's very important. This is millimeters, this is centimeters. I need to convert this to millimeters. This is 12.8. So the pressure of the gas is equal to 749 plus 128 millimeters of mercury. And so the pressure of the gas ends up being 877 millimeters of mercury. And so the correct answer is choice D. Correct answer is choice D. Okay, as you look at number 5, you can see that this was just a repeat of an earlier question. So this is a typo. I shouldn't have this in here. So I'm going to take this out, and I'm renumbering the rest of my questions. So this was number 6, but it becomes number 5. So number 5 now says, a compressed air tank carried by scuba divers has a volume of 8 liters and a pressure of 140 atmospheres at 20 degrees C. What is the volume of the air in the tank in liters at STP? Now, the first thing that you need to know as you look at this problem is you need to know the definition of STP. So STP is that, I just write here, STP stands for standard temperature and pressure. So that in STP, the temperature is 273.15 Kelvin. That's 0 degrees C. 0 degrees C, that's STP. And the standard pressure at STP is 1 atmosphere. So you're given the standard pressure. Now, as you look at this, we have air under this compressed air under this condition, and then we're going to change the conditions to STP. What equation do you use whenever you have a gas under two sets of conditions? You use the combined gas law, which is P1V1 over N1T1 equals P2V2 over N2T2. Now, as I look at this, the volume is changing. In fact, that's what we're looking at. The pressure is changing. The temperature is changing. But what does not change? It's the number of moles. This says you have air in the container. What would the volume of that air be at STP? So it's the same number of moles. The number of moles is constant. N1 equals N2 equals a constant. What can you do if you have a constant on both sides of the equation? You can cancel it out. So this says, what is the volume at STP? We're looking for V2. And so I'm going to take this, and before I plug the numbers in, I'm going to rearrange and solve for it. So V2 over on this side, this is equal to P1V1 over T1. And I'm going to divide both sides by P2, and multiply both sides by T2. Bring T2 up here. So see, my units of pressure will cancel, my units of temperature will cancel. I'll end up in the unit of volume. So the original pressure was 140 atmospheres. The original volume is 8 liters. Now the new temperature, T2, is 273.15 Kelvin. Now the main thing you've got to do with gases is to watch your units. The original temperature, T1, is 20 degrees C. Now I've got to express degrees C in Kelvin. 20 plus 273.15 equals 293.15. Now it's only precise to the ones place, but we'll write this entire number, 293.15 Kelvin. And the new pressure, P2, is the STP pressure, which is 1 atmosphere. Now look at the units. If you set this up correctly, the units will all cancel appropriately. Atmospheres cancels, Kelvin cancels, that leaves it in liters. And so the new volume, V2, calculates out to be, you're going to only have two significant figures. 8 has two sig figs, this has two sig figs. It will be 1.0 times 10 to the power of 3 liters. It'll be 1,000 liters to two significant figures. 1.0 times 10 to the power of 3 liters. So E is the correct choice in this answer. Okay, let's go to the next question. You have a 5-liter steel cylinder, contains oxygen gas at this pressure and this temperature. What mass of oxygen gas is present in the cylinder? Now notice you have the volume. Let's list what all we have. We know that the volume equals 5 liters. We know that the pressure equals 75 atmospheres. We know the temperature is 25.0 degrees C. Now we add 273.15 and we get 298.15 Kelvin. So remember, with gases you always express it in Kelvin. Now look, I know 3 of the 4 variables. The only one I don't know is the number of moles. There are 4 variables that completely describe a gas. And the ideal gas law, if we know any 3 of them, we can calculate the 4th. So the ideal gas law says PV equals nRT. And I'm going to rearrange and solve for number of moles. It's PV over RT. Now I can plug the numbers in. The pressure is 75.0 atmospheres. The volume is 5 liters. Divided by R. The value of R will be given on the exam. It's 0.08206 liter atmospheres per mole per Kelvin. And divided by the temperature, 298.15 Kelvin. Now, if you check the units, you'll see that everything cancels appropriately. Atmospheres cancels atmospheres. Liters cancels liters. Kelvin cancels Kelvin. Mole is in the denominator of the denominator, so it comes up to the numerator. And N, in this case, calculates out to be 15.33 moles. Now that's 15.33 moles of oxygen. This contains this much oxygen. This says what mass of oxygen gas? This is moles of oxygen, O2. So we're not finished. We're going to say, therefore, the number of grams of O2 is equal to 15.33 moles of O2 times, and how do you go from moles to grams? You use the molar mass. 1 mole of O2 has a molar mass from the periodic table of 32.00 grams of O2. So remember that for O2 you use 32 grams per mole. This is oxygen gas. This calculates out to be 490 grams. 490 grams. Okay, so the answer right here will be choice E, 490 grams. The next question asks you what's the definition of pressure, and you need to know that pressure is defined as force per unit area. Force per unit area. So force divided by unit area, so the correct answer is number 7. I've changed the numbers. This is now number 7. The correct answer is choice E. Okay. Number 8. Here's an empty aerosol can. It says I've got the temperature, I've got the pressure. If the empty can is thrown into a fire at 475 degrees C, what is the final pressure in the heated can? Notice we're taking a gas under one set of conditions and we're changing the conditions. Which equation do we use if you take a gas under one set of conditions and express it and you change the conditions? We use the combined gas law, which is P1V1 over N1T1 equals P2V2 over N2T2. Now let's identify what is constant. So we're assuming the volume of the can is constant. What would the pressure be if you heated up the contents of the can? So we're assuming the can does not explode. This is going to show that it will eventually explode. But if the volume remains constant, V1 is equal to V2 equals a constant. We can calculate that out. Okay. We know the original pressure and the original temperature. What else doesn't change? The number of moles of gas doesn't change. We're not adding to the gas or taking away from the gas. So we have pressure related to temperature. Now, the next thing I want to point out, since this asks what's the final pressure, we're going to say that P2 is equal to, and I'll just multiply both sides by T2. So it's P1 over T1 times T2 in the numerator. So the units of temperature will cancel. Before we do that, remember what units must we always express temperature in? It's always got to be in Kelvin. And so to express the temperature in Kelvin, I need to add 273.15 to each of these temperatures. And so if we take T1 equals 25 plus 273.15 equals 298.15. That's the original temperature. T2 is going to be 475 plus 273.15, so that T2 calculates out to be 748.15 Kelvin. These are both Kelvin. Anytime you do a gas laws calculation, the unit of temperature must be Kelvin. Pressure can be any unit as long as you're consistent, but temperature must be in Kelvin. So now we can plug those values into this equation. So what was the original pressure? The original pressure is 1 atmosphere. But the new temperature is 748.15 Kelvin. And I divide by the original temperature, which is 298.15 Kelvin. So my units of Kelvin cancels. I end up in units of atmospheres. And this calculates out to be 2.51 atmospheres. By the way, this is why you would never throw an empty can into a fire, because if it's empty, it still exhibits 1 atmosphere of pressure, and as it heats up, it will build up a high pressure and explodes. So the correct answer to number 8 is choice C, 2.51 atmospheres. Okay, we'll go to question number 9. Now, I've renumbered the questions. It was question 10, but I took out that redundant question, so now I'm calling this question number 9. The pressure of a sample of carbon dioxide gas in a 150 milliliter flask at 25 degrees C was found to be this. What pressure is exerted by the same quantity of gas in a different volume and a different temperature? We're taking a gas under this under two sets of circumstances. If you change the conditions of a gas, what's the best relationship to use? The best relationship is the combined gas law. So we've used this a bunch of times. This is very useful. P1 V1 over N1 T1 equals P2 V2 over N2 T2. Now, is there anything constant that we can identify? Well, this says the same quantity of gas. The same quantity of gas. That means the number of moles is the same in both cases. So the number of moles under condition 1 is equal to the number of moles under condition 2. That's a constant. You can cancel it out. Now we have a volume, temperature, and pressure. So the temperature and volume are changing. What would be the new pressure? So we're looking for P2. My suggestion when you have a plug and chug equation is to write the equation down, get rid of any constants, and then rearrange the variables before you plug the numbers in. You're less likely to make a mistake. P2 equals P1 V1 over T1 times, and I'm going to divide both sides by V2 and multiply both sides by T2. T2 over V2. So we plug in the original pressure. The original pressure was 637.4 millimeters of mercury. The original volume was 150 milliliters. But the new temperature is going to be 100 degrees C. Now, what do we always have to do with temperature? We've got to convert it to Kelvin. So this is 373.15 Kelvin. So I'll put that here, 373.15 Kelvin. And then we'll divide by the original temperature. The original temperature was 25 degrees C, which is 298.15 Kelvin. So we'll have 298.15 Kelvin. And what is the new volume? The new volume will be 250 milliliters. Look, I don't have to convert volume to liters. If this is in milliliters and this is in milliliters, they act as a ratio, and that will cancel out. So milliliters cancels. And the temperature in Kelvin, that cancels. And that leaves the unit of pressure, millimeters of mercury. So all we have to do is multiply that out. And when we do that, whenever we multiply this out, we will get 478.6 millimeters of mercury. And so the correct answer is choice A. The correct answer is choice A. Okay, the next example is a gas stoichiometry problem. What's the first thing you always have to have for any gas stoichiometry problem? Well, you have to have a balanced equation. Now, in this case, you're given the balanced equation. I'm going to list what's given here. It says, what volume of oxygen gas, so I'm looking for the volume, measured at 25 degrees C and 760, so this is 298.15 Kelvin. I convert 25 degrees C to Kelvin, and 760 millimeters of mercury would be produced by the decomposition of 10 grams of potassium chlorate. Now look, I'm looking for the volume. This is the temperature. This is the pressure. There are four variables that completely describe a gas. If I know three of them, I can calculate the fourth. If I knew the number of moles of oxygen, I could use the ideal gas law. Over here, let's write the ideal gas law. PV equals nRT. To get the volume of oxygen, the volume is equal to nRT over P. Now, I know R, it's a constant. I know the temperature, it's 298.15. I know the pressure, it's 1 atmosphere. Let's just rewrite this as 1 atmosphere. So all I need to know is the number of moles of oxygen. Well, this is a stoichiometry problem. The number of moles of oxygen, I'm going to start with 10 grams potassium chlorate, KClO3. And I'm going to go from grams to moles using the molar mass. And the molar mass is given. There are 122.55 grams of KClO3 per every 1 mole of KClO3. So I convert it from grams to moles. What is the next step always in every stoichiometry problem? It's to wake up screaming mole-to-mole ratio. So in the denominator, I have 2 moles of KClO3. That's so that moles of potassium chlorate will cancel. And in the numerator, I'll have 3 moles of O2. So this will give me the number of moles of O2. So when we calculate this out, the number of moles of O2 is 0.1224 moles of O2. So all I have to do now, I know everything. I plug it into the ideal gas equation. Let's see if I can, I didn't leave quite enough room to do this, but the volume is the number of moles, so 0.1224 moles, times R. The R constant will be given on the front page of the exam, 0.08206 liter atmospheres per mole per Kelvin. And I'm writing the units to make sure you use the appropriate units. Times T, the temperature must be in Kelvin, and the temperature in Kelvin was 298.15. And then divided by the pressure. And the pressure, I need to use atmospheres because I have liter atmospheres in this value of R. So atmospheres is 1 atmosphere. So look at the units. Moles cancels moles, Kelvin cancels Kelvin, atmospheres cancels atmospheres, and that leaves units of liters. And when we calculate this out, it calculates out to be 2.99 liters. So volume equals 2.99 liters. And the correct answer is choice D. Okay, number 11. Now let's just draw a picture of this. So we have two different 1 liter flasks. So over here, this is a 1 liter flask, and we'll label this A. A is present in here. It's 1 liter. It has hydrogen at STP. Next, over here, we have a different gas. This is gas, this is flask B. And here we have, it's also 1 liter, but this is chlorine at STP. So we're asked to determine the relationship between these two gases. Now the main principle here is, the important point that you have to know is that the average kinetic energy of a gas depends only on the temperature. So that's the important point. The average kinetic energy of a gas depends only on the temperature. Now, as we look at choice 2, Roman numeral 2, this says the average kinetic energy of the molecules in flask A is the same as the molecules in flask B. That is a true statement. That's a true statement because they're both at the same temperature. The temperature is 273.15 Kelvin. Here, and the temperature is 273.15. It doesn't matter that one has hydrogen and one has chlorine. They're at the same temperature, so they have the same average kinetic energy. Okay. Now let's look at number 1. What about the velocity? Well, you remember that kinetic energy is equal to 1/2 mass times velocity squared. Now this is the energy of one particle. What I highlighted here is the average kinetic energy of all of the gas particles. But this relationship is still true, that if I have two particles with the same kinetic energy, but one has a lighter mass than the other, what must be true of the velocity? If they have the same kinetic energy, then the one that has, where the mass is lighter, must have a higher velocity. The one with the heavier mass has a slower velocity. And so hydrogen is much lighter. The molar mass of hydrogen is 2. The molar mass of chlorine is much heavier. The molar mass of chlorine is 71 grams per mole. This is much heavier. This is a very light gas. Since hydrogen is very light, but it has the same kinetic energy over here, then it must have, it must have a much higher average velocity. And so the average velocity of molecules in flask A is the same? No, that's a false statement. This is false. The molecules here are moving faster. The hydrogen molecules are moving faster. They have the same kinetic energy, but kinetic energy and velocity is not the same. So 1 is false. Now let's look at Roman numeral 3. The number of molecules in flask A is the same as that in flask B. They're different molecules. Is that a true statement? Well, let's go back to the formulas that I encourage you to learn, the relationships. Avogadro's law says the volume of a gas is directly proportional to the number of moles if you hold the temperature and pressure constant. It doesn't matter what the gas is. If I have two gases at the same temperature and pressure and the same volume, they'll have the same number of moles. This is a true statement because of Avogadro's law. So Roman numeral 3 is also a true statement because of Avogadro's law. So the correct answer, Roman numerals 2 and 3, so that would be choice C. They're both true. The next question says, a gas mixture consisting of nitrogen, oxygen, methane, and carbon dioxide occupies this volume at this temperature and pressure. How many moles of carbon dioxide are in the sample? Okay, well, this is Dalton's law of partial pressure, that the total pressure is equal to sum of the individual pressures. I've got different gases in here. Now, actually, as I'm looking at this, there's an easier way to do this than Dalton's law of partial pressure. Here's the number of moles. Here's the volume, temperature, and pressure. If I think in terms of the ideal gas law, PV equals nRT. I know the pressure of this mixture of gases. It's 1 atmosphere. I know the volume of this mixture of gases, 9.60 liters. I know the temperature. I can find the number of moles, which is the total number of moles. So N, this is the total number of moles of all the gases, is equal to PV over RT. The pressure, I can just plug this in, is 1 atmosphere. The volume is 9.60 liters. R, the ideal gas constant, is 0.08206 liter atmospheres per mole per Kelvin. I'm just writing the units to make sure everything cancels appropriately. And then the temperature is 27 degrees C. Now, if the temperature is 27 degrees C, let's just jot down up here 27 plus 273.15 is equal to 300.15 Kelvin. So we'll have 300.15 Kelvin. Now let's cancel units. Atmospheres cancels atmospheres. Liters cancels liters. Kelvin cancels Kelvin. Mole is in the denominator. The denominator, it comes up to the numerator. So we multiply this out, and the total number of moles calculates out to be 0.390 moles. Now, how do I know this is the total number of moles? I mean, I've got a mixture of gases. It's because a mixture of gases obeys the ideal gas law just as an individual gas does. So this is the total number of moles. So therefore, the number of moles of carbon dioxide is equal to the total number of moles, 0.390, minus the number of moles of each of these gases, minus 0.1. That's the number of moles of nitrogen, minus 0.05. That's the number of moles of oxygen, minus 0.2. That's the number of moles of methane. And so this calculates out to be 0.040 moles. So choice A is the correct answer. Okay, and we have one more question here. This last question says, neon gas was observed to effuse 1.44 times faster than a certain unknown hydrocarbon. What is the molar mass of the hydrocarbon? Well, this is Graham's law of effusion. Graham's law of effusion is, we can express it this way, the rate of effusion of 1 divided by the rate of effusion of gas 2 is equal to the square root of the molar mass of gas 2 over the molar mass of gas 1. Now let's relate this to what we're looking for. We're looking for the molar mass of an unknown hydrocarbon. Now, if you're solving for an unknown and you have a choice, it's easiest to let the unknown be in the numerator. So over here, I'm going to put the square root of the molar mass of the unknown. That's what I'm looking for, divided by the molar mass of neon gas. And over here, this will be the rate of effusion of neon. There's this inverse relationship. Neon's in the denominator here, so the rate of effusion of neon divided by the rate of effusion of the unknown. So this is the relationship that we have. So neon diffuses 1.44 times faster than the unknown. So this tells us the rate of diffusion of neon divided by the rate of diffusion of the unknown is 1.44. That's equal to the square root of the molar mass of the unknown divided by the molar mass of neon. The molar mass of neon is 20.18, and that's grams per mole, and the molar mass of the unknown will end up being in grams per mole also. So I've just got to solve for the molar mass of the unknown. So let's square both sides. 1.44 squared equals the molar mass of the unknown over 20.18. Or the molar mass of the unknown equals 1.44, that quantity squared, times 20.18. And that calculates out to be 41.8, which to two significant figures, that's going to be 42 grams per mole. So that the answer ends up being choice E. Now notice this about this particular question. Neon diffuses faster. Well, that's because it's lighter. So if it diffuses faster and the molar mass of neon is 20, we could have gone through and automatically ruled out choice C and D. The unknown must be heavier. It diffuses more slowly than neon does.